Okay. So yeah, okay. Yes, I have shortened my talk. It was multiplicative parametrized homotopy theory using these or something. And so everything I'm going to say is going to work with Steffen Zagave, who's somewhere here. And we build a new model for parametrized spectra, which has good multiplicative properties. So in this day and age, I feel like I should justify why we build a model. So I will spend the first half hour trying to explain what we're trying to model and why we're building yet another model of it. And so the basic input for all of this, or the basic definition that one tries to aim at, is that of parametrized cohomology. So throughout B will be some space. Space can either mean topological space or visual set for now. And so just to remind you, a parametrized cohomology theory, is a functor. Well, it's a homology theory, a covariant functor is a cohomology theory, a contravariant functor from the category of spaces over B into graded abelian groups, such that it has the usual properties that I'm not going to spell out again. It's homotopy invariant, it commutes with direct sums, it has Mayer-Taylor sequences, so in particular you need a connecting morphism, and so on, such that I think you all have seen the definition of a cohomology theory. So let me give two examples, one just for shits and giggles, and the other one because it's going to be important for the rest of the talk. The first one is you take the automorphisms of some abelian group as the classifying space as your base space, and then you just send the space xt to the cohomology of that space with local coefficients a la Steenrod in the bundle E out M crossover out M, and that lives over E out M. So that's a perfectly good example that's been around since the 50s, and then slightly more recently, but this only works with X as a finite cell complex, is when you set B equal to the classifying space of a projective unitary group of a Z2 greatest Hilbert space. And I'll try to keep the sort of operator theory to a minimum here.
So you set unitary in the rules of formulas?
Yeah, I'm going to do it works in both real and complex coefficients. I'm going to stick to the real ones because I'm used to that. So this is a real Z2 graded Hilbert space, and then unitary groups are called orthogonal groups. And you can send one of these guys to its KK theory, or rather to the KK theory of the section algebra of the following bundle. The projective orthogonal group acts on the compact operators on your Hilbert space by conjugation. Take a compact operator, conjugate it with an orthogonal thing, you still have a compact operator, so you can form this bundle. Pull it back. That's a bundle of C-star algebras. You take its sections, that's a C-star algebra, and then you take its KK theory. And again, if you want homology, you put the C or the coefficients here, and if you want cohomology, you put the coefficients here. KK theory is bivariant. And
so you're implicitly pulling back to X, right?
Oh yeah, sure, sorry. I want to take the sections over X. That's what the map is for after.
Why does X have to be finite?
Because otherwise this will not be weakly equivalent, it will not satisfy the axioms I did not spell out.
It's not going to be weak homotopy invariant.
Yeah, it's definitely not going to be weak homotopy invariant, it's definitely not going to have another couple of good properties. I mean, if X is not at least compact, this is not even a C-star algebra because you can't put a norm on it, because sections can be unbounded. You need some assumptions, and the good ones are finite properties. Okay, so these are kind of the geometric examples that people wrote down in the 50s, 70s or something. And of course, homotopy theorists looked at this and represented them, and you represent them by parametrized spectra. That shall call the category of the loosely spectra over B. And the precise meaning of this category will change throughout the talk and become ever more refined. So in the beginning, these were just objects of the form. It's a sequence of spaces over B with a section and structure maps like this, sigma n, such that, well, first of all, it really is a section, and this map is fiber-wise. So Pn plus 1, no, Pn plus 1 sigma n is Pn. And this guy here is my notation for the fiber-wise mesh. So that just means if you take a fiber of this map, it's now a pointed space because you have this section to give it a base point, and then you suspend each fiber. So that's what this construction does. Okay?
You can sigma n is zero section.
Yes. Oh, yeah. That's also good.
Why do you need a section?
It generalizes pointed spaces.
Pointed space.
So these things were considered, I think, first by Hooper and Klapp, and somehow they built the usual. They showed that you can actually build cohomology theory out of the Adams type and methods. And the good examples you had of such spectra, at some point they were developed to represent these theories, are you can take if you find a model of the Amber-MacLane spectrum where the automorphism group n actually acts sufficiently nicely, then this is going to represent this example. And similarly, if you can build a nice enough model of the K-theory spectrum on which the projective unitary group, orthogonal group, acts in a good enough fashion, then you can build this as an example. So, and here I mean like forming these Borel constructions level-wise to represent this example. And somehow, this was the bane of my thesis. I went through lots of iterations trying to find this done in the literature, only to then do it myself. So this apparently took quite some time I couldn't find a correct model in the literature. But once you have these parametrized spectra, you can of course do much more general things. So this guy, I will denote by kk mod pure, the homotopy quotient of this action, and this will feature throughout the talk again. So the rest is sort of will slowly disappear. Okay, but once you have this definition with spectra, you can of course build lots more non-geometric examples of this. So for example, if I give you a ring spectrum, you can consider, well, the following not yet definition. You can try to take its units and build this spectrum, right, which wants to represent universally twisted R cohomology.
What is that letter?
Gamma.
Gamma.
Gamma, thank you.
Yes. So for universal bundle. And of course, as I stated, somehow if you have a ring spectrum, then what do I mean by ring spectrum and what is this? So somehow in the pre-symmetric spectra world, this could not really be done. And so this was formalized by May and Sigurdsson. So surprisingly, they don't really discuss it much in their book. So they made the category a little bit better. And then it's the exact receptacle for what I'm about to tell you. So they took the category I defined up there and added ON actions. Jesus Christ, my screen's at the board, it's really loud. ON actions on each EN. So if you look at this, what this means is that, and in such a fashion, of course, that this projection map becomes ON invariant, this lands in the fixed point, and this map becomes equivariant. So this is literally what you would define as fiber-wise orthogonal spectrum. And if you now take an orthogonal ring spectrum and you make it an omega spectrum, then I can take these away. And this will literally be a good object in here. Right? The units of an orthogonal spectrum are a group-like topological monoid sitting in degree as a subthing of its zeroth space. And then I can make this construction and it will precisely give me an object in here. So with that, they produced somehow the first rigorous model of this construction and somehow provided this with model structures so that you can actually write down what the homology and cohomology functors are in the usual fashion. So then there's several sort of problems with this. The first one's probably screamingly obvious to everyone who's ever worked with symmetric or orthogonal spectra. An orthogonal omega spectrum, like there's no commutative examples. So somehow this process, even if you started with a commutative spectrum, it can only ever be a positive omega spectrum.
Singular homology.
Sorry?
Singular
Yeah,
homology.
exactly, except the singular homology. So this construction, I mean, you can take any commutative ring spectrum, resolve it by an associative one that is an omega spectrum, and then from this, but you've lost all commutativity properties. So that's one of the things Stefan and I are going to repair. This gets a bit better. But before that, maybe, of course, nowadays, May Sigurdsson, this was in 2006, published in 2006. This is by no means the state of the art anymore. So if you go into infinity land, I will soon write down what this construction looks like there. None of this is a problem. You get coherently commutative objects. And in particular, you get the following example of twists. So somehow, why do we care about these theories? These are the universal theories where, say, vector bundles have Tom classes. And you have a Tom isomorphism, and you have Poincare duality. So every manifold determines a map into BGR1R. And with that twist, it then satisfies the homology is the dual of twisted cohomology. And all these things, they are true for this model of parametrized spectra, or for these parametrized spectra. But there's, so unfortunately, if I wrote this down, I would be out of time soon. I want to give another example of sort of twists that I learned from a paper of Ender, Blumberg, and Kresk, where they construct degree 4 twists of TNF. And that somehow happens in infinity land and goes as follows. If I give you an infinity map, then I want to end up. Then I can look at its Tom spectrum. That's going to be an infinity spectrum. In particular, I can take its BGR1. And now I want to provide you a canonical map from here into there, along which you can twist. The construction goes as follows. You can take the fiber of this map. And if you take the universal vector bundle over the O, you pull it back here, you get some vector bundle. But if you pull it back here, it becomes trivial. Canonically trivialized. So that means when I apply Tom spectra to this situation, I forget about this map, I here, by definition, get n theta. And here I get the suspension spectrum of that space. And now, in infinity spaces, the constructions of GL1 and suspension spectrum plus are adjoint to one another. So I can adjoin this construction and get a map. Like this. Get a map like this. And then I take the justifying space. So this is a very, somehow, if you plug in certain examples here, this is a very geometric way of producing, of probing this space, which is completely ununderstandable. But if you do this, you can, I mean, let's do an example. Let's take H to be split. What I do. And then what do these things look like? Well, here we have BGR1 of the sphere. And spin. And here we have B of spin. And what's the homotopy type of this? Well, O mod spin, I mean spin just, this is the lower two homotopy groups of O. So this has exactly two homotopy groups, and it turns out to be 2 truncation of PO. But then I can use this to do more. I mean, some of what this says is, a map into here is a first and a second Stiefel-Whitney class. And somehow this measures precisely, if you have a vector bundle, it of course comes with a canonical map into this space, and it will vanish here if and only if its first and second Stiefel-Whitney class vanish, which precisely says something is orientable in M spin if and only its first and second Stiefel-Whitney class vanish. And this is sort of the generalization from arbitrary time spectra. So map into here vanishes the canonical one, then you're orientable. But now you can use an arbitrary map.
I mean, does this really imply if and only if?
No,
I guess this implies one direction.
No, the canonical map from BO factors through that. So for vector bundles, it's the same.
I mean, I guess.
But in general, of course. You can now use, however, not just this to produce twists in cobordism spectra, but whenever you have an orientation of your cobordism spectra that's an E-infinity ring map, you can use it to produce twists elsewhere. For example, you can use the A hat gene, so the alpha orientation, the Atiyah-Shapiro orientation, to produce twists in KO. Right? So that's a good way of producing twists. And now I've given you, well, now I've told you that this entire BGL story, this universal bundle, can be modeled in infinity land.
Excuse me, is this with Kepler or is it
I thought this was rest. This is the degree 4 twist of TMF. I think that is. Sorry, David.
They also have a there's a later paper with Kepler, right?
I mean, I think all combinations of those authors have papers together. I think it's this one. Okay. Did I write it down in my notes? Oh. God damn it. Yeah, and in my notes it says Gärtner too. Really sorry, David.
Sorry for Charles.
Leave Charles as well. But
I mean, it's Charles' own fault, right? But so, over this space, you now have the universal bundle. I will tell you in a moment how it's built in infinity. So you can pull it back here. Sorry? Yes. Correct. So let's call this the tautological or lower twist of K theory. And now, if you know anything about orthogonal groups, maybe I should have said this first, but what is the homotopy type of this space PO? Well, let's take this. The orthogonal group of an infinite dimensional Hilbert space is contractible. That's Carter's theory. But I have a Z2 graded Hilbert space, so it actually has 2 contractible components. And then I projectivize those. So that means I've added a second homotopy group. So the space BPO which this spectrum lives over, has 2 homotopy groups, Z2 in degree 1, Z2 in degree 2, and now I can wonder what the K invariant is. Turns out the K invariant is non-trivial. So this space is the same as the space we found here. And you can ask the question, KO not PO, not ask it in grammatically correct form, is that spectrum, that parametrized spectrum, the same one as if I take the universal bundle and put it back here? Call this tout KO. This is tout. And to my knowledge, this question has not been answered in the literature before. This is somehow, I mean, you could ask this question about 10 years ago, and I don't think it has been done. And one of the things that immediately pop out of the model, out of this model that I'm building with Steffen, have built with Steffen, is that the answer is yes. And more, it's true as infinity parametrized spectra. So that's somehow an immediate application that pops out of our our result that I sort of want to advertise. In particular, I claim the left-hand side has an infinity structure and the right-hand side has an infinity structure, so I better explain that, and that's somehow something I will do in infinity land, then explain why it's not possible yet in one land, and then explain why it is possible in one land. Okay, so how do you get the somehow, if I just consider parametrized spectra as the underlying infinity category of this, and this is well known to be just functors from B into spectra in infinity land. And if B is an infinity space, then this category carries two symmetric monoidal structures. And this statement only makes sense for one of them. So if I give you two such spectra, I can build a new functor. I can build a new parameterized spectrum. Right? That's what I called bar smash before. That's the exterior product. And now I can do two things. I can either pull it back along the diagonal to get something one would probably call smash over B. And the analogous symmetric monoidal structure to this in the category of orthogonal symmetric spectra, orthogonal parameterized spectra was studied by May and Sigurdsson. One of the problems is if you look at it, our smash product is a colimit process, pulling back is a limit process, so they don't really interact well, and on the model category level they get horrible properties for that thing. So they somehow got stuck in the analysis of the ring spectra for this. But that's also not what I want to talk about. There's a second monoidal structure. Somehow this also didn't use the infinity structure at all, this you have for any space. But if your space is infinity, you can use its multiplication to map this space back to B and come instead. And since I'm famously bad with left and right, is left correct or not?
Yes.
This is just Day-convolution. Sorry? Good. That's left for you. Right, this doesn't really have a name as far as I know.
What's bad with convolution?
What's this? It's a long symbol, convolution. It has a, yeah, I can bring the symbol.
Convolution is no left and right.
Okay, and so the statement is, if you now look at this universal example, gamma r in the infinity land, it is the infinity for this second monoidal structure. This minus 2. Okay? This fact somehow, if you don't just consider the universal bundle over BGR1R, but rather over PIC, it becomes a bit more obvious that it's so tautological that I can't possibly explain it. And if you try to produce a monoidal structure here, you'll fail. So somehow, for those who know this, and to the others, take it as a fact. So it's this monoidal structure for which you can even ask the question whether these two things agree. But unfortunately, the May-Sigurdsson category, it does not have an analog of this monoidal structure. Unless B is a commutative monoid. Right? If you look at the definition, if you want to make this a one-categorical symmetric monoidal structure, you're pushing something forward using the multiplication of it. That's supposed to be symmetric monoidal. This push forward had better be symmetric in the end. So you better have a commutative monoid. But a group like commutative monoid is always lambda MacLane, and BGL1 is almost never lambda MacLane. So somehow this infinity structure, in which this universal thing is the infinity you cannot model in that Macy-Goodston category. So that's somehow the basic problem Stefan and I addressed, and somehow, to say why do we do this, for example, we get a pretty topological proof of this right up. And this I don't know how to do in infinity. Not
Sorry, you don't know how to do it in?
infinity land. Somehow you'll see how the proof works. It's not really tied to it, but I will use models for the spectra. And somehow some of these models are now available through the work of Thomas and Markus Land, but some of them I don't know how to produce. K-theory, they've recently produced K-theory spectra in a purely infinity categorical fashion, where you can state this question now, but somehow for the answer I will try to give, this is not sufficient. Okay, so much for the motivation. Now come the actual definitions and the category we actually consider. So it's fairly simple. You take symmetric spectra, like Hovey produced a general machine. If you give him a model category, he gives you back a category of symmetric spectra in that model category. As long as it was monoidal, and you gave him an object as well. So what do? We take the category of retractive spaces. This is the name Stefan taught me for this. So this is spaces over and under that consists of diagrams like this. In this, rather I should rewrite this like this. In this we have the fiber-wise smash product, the external one, so that crosses the base space and takes fiber-wise smashes of the fiber.
What's the symbol on the R?
Symbol on the R.
I'm sorry.
An R.
What does this have to do with the thing that's retractive?
Retractive. No, it's all retractive spaces.
Ah.
It's all retractive
It's
spaces.
allowed to vary. That's
Exactly.
quite important.
Yes. Thank you. That's going to be the whole point.
Thanks for making that clear.
Yes. It's not retractive spaces over B. It's retractive spaces.
Not over X.
Yeah. Over X. Okay. And I give you an object. S1, point.
Can you repeat the definition of the smash again?
So if I give you two things, then
Different structure.
no, I couldn't possibly. I'm not going to write down the actual definition. So what this is the thing. There's a unique thing which on the base of these things is the cross product, and on the fibers is the smash product, and it has a total space. Okay, so you can write that total space down. It takes a while.
Right, it's a simple co-limit of from products of the B's and the D's. It's not so mysterious.
No, it's not mysterious at all, but somehow. Okay, in any case, that's the symmetric model structure. Is that okay? So-
Raise it.
Sorry?
I was just making fun of it.
Yeah.
Sorry.
That part is clear. Okay, so Hovey defined this category and provided two things. He provided a model structure. Let's say it like this. So the category of retractive spaces has a standard model structure in which a weak equivalence is one. That's a weak equivalence on both base and total space. And the fibration, well, it's what you would expect somehow. And the cofibration, it has an easy model structure. That's not well on it. So Hovey provides then a model structure on this category and an extension of the smash product. And I claim this category modeled in a very good fashion, not the category of parametrized spectra over some particular space, but the category of spectra over an arbitrary base space, and then very easily this symmetric, somehow the extension of this smash product precisely becomes the structure here, and not the one by one. Okay. So that's what I want to convince you of in the next half. So let's see what an object looks like. What is a symmetric spectrum? Well, it's a sequence of spaces, of objects in the category. So in this case, it's a retractive space. I will suppress the structure maps from notation. Together with sigma n actions and structure maps like this, and this has a n+1 action that I could vary. In particular, if you stare at what happens at the base space level, then as I said, this symmetric monoidal structure just crosses the base spaces, so it does nothing. So what you see is that the base space they precisely form an I space. You have a space, a sequence of spaces with sigma n actions and canonical inclusions from one to the next. That's precisely, that are equivariant for this action. That's precisely what an I space is.
But they don't have to be inclusions.
No, maps. Maps, yes, absolutely. That's precisely what an I space is. And they are also not inclusions. So what we obtained is a functor, the base projection from, so I will define, this is the category of symmetric retractive spectra from the type. So we have a base projection. You choose.
The sigma n action is over xn or xn?
No, it's on both. And both maps are supposed to be equivariant.
Okay.
That's the whole difference to the May sequence. Exactly. And we define, so now we can define the category of spectra parametrized no longer just by a space, but by an I space. That's symmetric spectra over B as the fiber of this thing of B for some I space B. And I propose this as a replacement for the category of spectra over B. In particular, if you've ever worked with I spaces, now in order to get such a structure, you need a commutative I space. And luckily, many infinity spaces have good representatives as commutative I spaces. In particular, GL1 does by work of Schlitt. So that's somehow what's behind this idea. And if B is constant, that hopefully answers your question again, then that precisely says these maps are trivial, and then this is exactly the category. So this is the symmetric version of receiver. But in general, you can just plug in a non-constant I space. So in order to get anything to work, we need to put model structures on these individual categories, right? We had Hobby provides one on the big category, but we also want them on these individual categories. So
it's made service if you've done this with orthogonal as opposed to symmetric.
yes, it's the symmetric version of May sequence.
You could also do it orthogonally?
I mean, this definition, I'm sure you can. I have not thought about how you raise the model structure, but I mean, it's more. Right? Orthogonal is always a bit more complicated because you need more assumptions on your original category. Sigma n, I mean, I need to make a set of continuous.
Well, the original category is spaces.
Yeah, I assume all this works. Yes, but I mean, also, as you can probably tell, if you know me or Steffen, there's a relatively clear division of labor within this project. But
Steffen doesn't work. And you can
do I hear jealous? So each of these categories inherits a model structure. From the category of retractive spectrum. And by this I mean you literally take just those maps. I mean, this is a subcategory in here, you literally take all maps, cofibrations, fibrations with equivalences that are so here from the model structure. But nevertheless, this is not a trivial statement. Because if you, I mean, the lifting properties that you have in the model category, they're of course all satisfied. But when it comes to factorizations, if you look at the argument that Hobby uses to produce factorizations in here, if I give you a map which happens to lie in here, the factorization has no reason to lie again. So you need a completely different mechanism of factoring maps. So this looks more innocent than it is. But then, once you have that, you can recover the big category as the Groton deconstruction of the functor from I spaces to categories that send an I space B to the category of spectra over B. And I don't mean this as categories, I mean this as model categories. I also mean, I don't just mean it as categories. So, Jonathan Hapas, hopefully I get it correct this time, and Matan Plasma, they've recently written a paper a few years ago that looks at the Groton deconstruction in the context of model categories. So maybe I should rewrite model categories. Right? And if you take their Groton deconstruction applied to the usual model structure on I spaces and to this restricted model structure on this, then you literally get back the model structure Hoppe constructed for you. And here I don't mean equivalent equivalents. I mean equivalence of categories that carries the model structures to one another. And so now this result then, using known comparison results, this immediately implies that this Groton deconstruction is also the infinity categorical Groton deconstruction. And this category really is the infinity, I mean the parametrized spectra as you would define them in infinity land. So somehow these two results together show that the underlying infinity category is the one you want, and somehow you can model the things that happen in infinity land quite nicely. And similarly, if X from B to B prime is a map of I spaces, then you have two functors, spectra over B prime, spectra over B. Namely, in this way you have pullback, and in this way, well, okay. Thomas scolded me for calling it shriek the other day, so maybe I'll call it natural. It's the left adjoint of pulling back. These are equivalent. So that's quite nice. And if this map happens to be an I equivalence, then they're actually equivalents. So plus an equivalence if F is an I. And furthermore, the pullback functor, say in simplicial sets, also has a right adjoint. And that right adjoint is usually denoted F lower star. This is not equivalent, but we can show it's right derivable. Okay. So this has all of these things are somehow as good as you can.
The abstract Kahn extension exists.
Yes, which you can also immediately deduce from infinity land. So somehow, I mean, we give a simple formula for this. You have to factor it as a, well, not so simple formula. No, the formula is quite simple. The proof is not.
Formula, but it's not.
Okay. Somehow you have to factor it as an acyclic cofibration into fibration, and then for the acyclic cofibration part, you use the left adjoint, and for the other part, you write it down.
To either clarify or spread confusion, you should highlight that the objects in this category of symmetric spectra relative to B, these are not symmetric spectra with values in some category. So the different levels of the symmetric spectra live in different categories. So the nth level lives in the category of spaces over and under the evaluation of the base space at n. So which is why we take this detour.
This was going to be my next example. So as a corollary, I mean, somehow, yeah, maybe I would have forgotten anyway. But what you immediately get out of this is that if D is a commutative I space monoid, then spectra over B with two formats monoidal model category. i.e. the push-up product axiom. I mean, so I didn't say this, but Polly also verifies the push-up product axiom, and you can trace through all of this and form monoidal model categories. Okay, and yes, as Stefan said, this is precisely interesting when this is not constant, and if B is not constant, then symmetric spectra over B are not symmetric spectra in some category. So this is somehow a weird hybrid category built out of all the all of these retractive categories over the various spaces in the I space. Okay. In particular, this holds true for the model that schlicht, if you give me a commutative symmetric ring spectrum, then there's this model for the BGL1 of it that is again a commutative I space, and with that structure you can now try to model the E infinity, the infinity structure of this universal R model that I detailed earlier. And so maybe let me first remark, though I will not make this much more precise.
Your category is symmetric model, right? Or
Yes, absolutely. Yeah. Absolutely, that's the commutative. Yeah. So now we can lift the model structures to commutative objects using the work of Schollbach, Pavlov. So using Pavlov Schollbach. Positive version. To commutative objects. So maybe this is also more a proposition. This happens. Okay, and then you can make a model, a simple one, for this universal gamma construction. The functor that takes a commutative symmetric ring spectrum and spits out a commutative object in retractive spaces. It takes such a spectrum and sends it to the bar construction of, you take the suspension spectrum of PL1R acting on R. That models this gamma. Is derivable and models the gamma construction that I gave before. So somehow we've realized this as a map from commutative things to commutative things.
Okay, may I ask one question about
Sure.
the thing you're just raising? Just out of curiosity, when you say you also get from this Harpaz-Brashma this comparison to the parametrized like infinity spectra?
Yeah.
I mean, now you tell me that symmetric spectra over B is not quite. I mean, how do you see that?
Because it's an because any I space is I equivalent to a constant.
Right. So for every pair of I spaces, it's clear that the functors agree, but you're making a coherent statement.
Every pair of functors, it's clear.
I mean, you're saying something like this will be a functor from the base into somewhere like this Grothendieck unconstruction or whatever. How do you know it's equivalent as a functor?
Maybe I cannot. You're right. The problem is somehow. Yeah, maybe you're right. So what I wrote on the board is entirely correct, but so that's yeah.
I mean, I don't doubt that they are equivalent.
No, sure, they definitely are. But yeah.
We have this burden of proving stuff.
Yeah.
It's annoying, right? Can't we just say infinity?
I mean, this is like this appendix, right? And you told me it's a non-trivial theorem.
Okay.
I mean, this doesn't imply this.
It doesn't imply, but it's of the same kind. It's the same flavor, and you told me it's a non-trivial theorem. This is more general.
So, I mean, it just
Fabian, you were about to mention that the underlying commutative I-space monoid of the star construction is a usual PG.
Yes. Oh, should I? Where is it here? Oh, this as base. Use an I declaration. The base space of this, if you just go through the definition, is precisely the usual I space degrouping of the GL1. Okay, but so this recovers the constructions, or this gives a version of the constructions that you can do, that I touched to before, but now we can do a new construction. And that's going to lead to the proof of the result. I said at the beginning this question about the two models of K. Namely, if I give you a functor from I into groups, by this I mean topological groups, and a commutative ring spectrum, then you can form plus actions correspond to G from Gn plus Rn into Rn, satisfying a bunch of conditions. Maybe the time, maybe I'll just give them in words. Somehow they should be sigma n equivariant for the obvious diagonal sigma n action you have here, and they should preserve the base point in here, and most importantly, there should be somehow, because you have a multiplication in the group and a multiplication in the ring spectrum, if I give you 4 elements, 2 in the group, 2 in the ring spectrum, you can either first multiply in the group and in the ring spectrum, and then use the action, or you can first use the action twice, and then multiply the ring spectrum. Those 2 ways should agree. So, if this condition is met, we can form what I want to call R mod mod G, the spectrum given by the usual degree-wise buff construction. This inherits structure maps from R, and so this is an object in this category of retractive symmetric spectra. And if the group, furthermore, this I group, has the property of being I-commutative, which means that it doesn't mean that it lands in commutative groups. It means that the nth, somehow, the Gn and Gm commute in Gn plus n. The typical example of this is sigma n's. The sigma n's form an I group, and somehow the block sigma n and the block sigma m in sigma n plus m commute with one another. So if you have one of these, then this spectrum will actually be, again, a commutative a commutative ring object, commutative monoid object in this category. And in particular, this construction you can use to model things like K mod mod PO that I had at the beginning. And so we want to produce a comparison theorem between this type of object and this type of object. And we do. So for that comparison theorem, I need one more ingredient. That is due to Marek Stadalat and Ulrich, who first studied such actions and termed them Ekman-Hilton actions. And that's a fairly simple one. Namely, this also determines a map of G into GL1R. And that map, so recall that the nth space in GL1IFR, that the nth space of this is the subspace in loops n Rn, those path components in here which map to units in the base component of the, in pi naught of the rings. And you can just take, so we call that map UB, and it takes an element G and maps it to the loop that sends S to G times the unit applied to S. Okay, and with these ingredients, I can now state the second theorem, which compares these instructions. Namely, on the one hand side, so if I have the situation given above, I can form this spectrum, and on the other hand, I can use that map to pull back that universal bundle. And they sit in a one-step zigzag with an obvious middleman, namely, I let this G act on the ring spectrum through this map. Okay. So there's an obvious comparison map here, which just consists of applying that map in each degree of this bar construction. That has base component this, and therefore maps to the pullback. And this is a comparison map between two bar constructions. Somehow, if you remember, EGN and BGN are also built using bar constructions, and somehow, I mean, this is not the bar construction of a symmetric monoidal structure, this is the bar construction of a monad, but somehow there's a transformation of monads that's easily written down that produces this comparison map. And this map is a weak equivalence that are sentence, the comparison maps are weak equivalences. Well, not as is, but when we derive this construction and derive this construction. Crucially, do not derive this construction. Let's put the condition on that R and G are positively fibrous. And that, in this case, means this guy is a positive omega spectrum, and this group is homotopy constant from degree 0 on. So all its structure maps are homotopy equivalents.
One.
Sorry?
From degree 1.
From degree 1, except the ones coming out of degree 0. Exactly. So this precisely says this is the object that models universally twisted R cohomology, restricted to some subgroup, and this is a spectrum we might build geometrically. And now, in the last 5 minutes, I want to sketch how this.
What is derived in this derived thing, and what is
everything? I mean, so the gamma R construction is derivable. This is a functor that's right derivable, and you do that. And similarly here. So in order to form this bar construction, you should replace G cofibrantly.
and then replace R?
No, if one of them is cofibrant, that's it. Okay. But somehow this object is basically of no interest. This is just to facilitate comparison. Yeah. And somehow this functor, I wrote it's derivable, but it's neither left nor right derivable because you have to replace G cofibrantly, but before you can do that, you have to replace R fibrantly to form GL1. So it's a,
What's the meaning then of derivable?
you can do that and it becomes homotopy coherent.
I would
you can
say
do that.
In sense,
Yeah, there's a homotopy
state
invariant state.
equivalences from R to R prime to the equivalences of the gamma R's. So it's a homotopy invariant construction.
It's already homotopy, that's what it's saying.
No.
And you have to assume that R
That's
is
why we want to spell
level
it out.
fibrant and semi-stable. And
But you know,
then you have to still take a cofibrant replacement of the units to make the bar construction a homotopy invariant.
so you have a function between relative categories, so it makes sense to ask if it's left or right derivable in the infinity sense. Is it?
Well, it's a two-step process, this functor. And the first part of the process is left derivable, and the second part of the process is right derivable. But then the composition is neither. So it's a composite of a left derived and a right derived. Okay. That's okay, so let's do the final example that has to do with this PO group and K theory. And so I give you a I-commutative I group. And you consider the following group. This is the orthogonal group of a certain Hilbert space, regarded as a Z2 graded Hilbert space, tensor the Clifford algebra. Okay. Again, this is supposed to be the graded orthogonal maps, so this has two contractible components. But from this, I can now build several other things. So this certainly defines. So this is not. No, this is supposed to be a squiggly O, but I'm having a hard time with the font. And the actual O will appear now. That's a bit annoying. So you can look at the even transformations in here, and as I just said, they are contractible. except in degree 0. Oh, in degree 0 there are points. I can embed this into the complete I group, and I can mod out the projectivization. And all of these are somehow, well, they're obviously positive fiber. But now, into this I group, I can embed the pin group. Right, the pin group, pin n acts on Rn, so it acts on the functions on Rn, and it acts by multiplication on the Clifford algebra. So this produces an inclusion here. It maps the element -1 in pin to minus the identity. So in particular gives me a map from the usual orthogonal group with no squiggles into PO, and it restricts to an embedding of the spin group into OI. And so in particular I can use the space O, the even operators here, modulo the spin group as a model for B spin, and thus build a spin coordinate expansion. This is a definition originally due to my advisor, Michael Joachim. I can define the spin spectrum as, well, maybe I write down the bundles first. So now if you now look at the space POI mod OI, this is the same as the space OEV I mod spin I. And as I said, this is a model for B spin. So over this you have the universal bundle. And this model for M spin, you literally take the Tom space of this. So he showed that's a perfectly good symmetric ring spectrum that represents spin balls. But you can immediately see, probably, that the PO-I group acts on it. And I claim that this action satisfies all the assumptions I didn't tell you about. So we can use this to build a model of spin n mod pi. But to this model, we can now do the construction of tautological twists. So what does that look like? Well, that meant I had to take the fiber from B spin into BO. So I have to find an object like this. But this is just that group itself. I have a map from the orthogonal group into this, and because this only has two homotopy group, that canonically factors over the spin group. And over here, I of course have the trivial bundle. Okay? So if I now do the tautological construction, the construction of tautological twists, I get a map out from POI into GLI M spin. Somehow you can check that this tautological construction works equally well in this island. And now it's a simple check that this map is not somehow homotopic, it is equal to the flat construction of the action map. So what this gives us is so to this comparison, I can now apply theorem 2. And this says that M spin mod PO, I get a comparison zigzag to the pullback of the tautological bundle over M spin. Well, derived. And, well, I'm not going to do that anymore, but there's a similar model for K-theory on which PO acts very naturally. And the alpha map, and again, that model is due to my advisor back in the 90s, and he showed that there's a canonical map of ring spectra from here to here that is, and you just check, it is actually PO equivariant. So you get an induced map on these spectra. By the comparison theorem there again, you get a map from what I earlier called out KO upper star of gamma KO. And while the spin spectrum is certainly not positive fibrate, the KO spectrum is. So the theorem applies that these two are good. So that's the proof, which is now very quick, of the result I spoke of here. And I'm sure the conditions of positive fibrate here are much too strong. Something like semi-stable should suffice. I'm sure this map is a weak equivalence as well. But for the application, this suffices, so we can check that. Thanks for your attention.
So we say semi-stable is enough, then with orthogonal spectra it should be one in complete generality.
Yeah.
The other thing is, a lot of your arguments, and that's maybe it was the point, are point-set level arguments.
Yes.
You work with orthogonal objects and so on. So all these things actually represent equivariant homotopy types. In fact, global homotopy types. So I mean, you're proving equivariant statements because, which you wouldn't if you did this all in infinity. But
maybe.
What's the equivariant content of this?
I do not know. I mean, the weak equivalences are then finite, right? And so questions of this form are. I mean, we show that weak equivalences on the, well, in our definition of weak equivalences, and if you give me a finer definition of weak equivalences, it might break. Right? It might be true, might not be true. So, I do not know. This could be, it's a, yeah, full stop. I just do not know. But somehow, note that this type of action is quite different from an orthogonal, from an equivariant spectrum. This is, so, somehow.
No, but that's, the G is a global group object. The R is a global object. It's a global action. You shouldn't look at it level-wise.
Yeah.
It's sort of as n exhausts the universe.
Yes. Yeah, it is.
So
I mean, yes.
global group acting on a global ring spectrum.
Global for finite subgroups.
Or you can do this orthogonally.
Yes.
I suppose.
But is it known also that I spaces are modeled for unstable global spaces?
I'm pretty sure. I don't think it's. Steffen? I'm pretty sure. Markus Hausmann's thesis is done unstable. He does it for symmetric spectra, unstabilized.
Answer is I do not know.
Anything else? Let's thank the speaker again.